Hello everyone, welcome to this tutorial on fundamentals of heavy trails. Professor Jayakrishnan Nair received his BTech and MTech in Electrical Engineering from IIT Bombay and PhD from Caltech in 2012. He has held postdoctoral positions in Caltech and CWI at Amsterdam. He is currently an associate professor at EE department in IIT Bombay. His research focuses on modeling, performance evaluation, and design issues in online learning, queuing systems, and communication networks. By drawing on tools from stochastic modeling, queuing theory, game theory, optimization, and control theory. His recent interests include network economics and uncertainty management in smart grids. Welcome, Professor. Looking forward to tutorial.
Okay, so yeah, to begin with, I do have slides here, but these slides aren't the versions that I had actually prepared for the tutorial because there was some issue porting it from my laptop or something. So I'm going to use the slides largely as to show the occasional picture, but most of it is going to be board work. So again, these slides are an earlier version. So not transition happening. This is the wrong application. Okay, fine. All right. Yeah, so let's begin. So this is going to be a tutorial on heavy tail distributions. So why is there a tutorial on heavy tail distributions? Well, we are writing, the book is actually out, and talk about the book later. Why a book on heavy tails? Because as I will point out, heavy tail phenomena are ubiquitous, but they are also fairly misunderstood. They come up all over the place. For example, in several networking applications, whether it is social networks or technological networks, heavy tail degree distributions, for example, come into the picture. Internet file size distributions tend to be heavy tail. I haven't defined heavy tail yet. We'll do that in a bit. If you look at wealth distribution, across human beings, that distribution tends to be extremely heavy-tailed. Losses because of natural calamities like earthquakes or other such natural catastrophic occurrences, losses, whether it's loss of life or loss of property or whatever, all of these things tend to be heavy. But because of the nature of these distributions, because of the fact that they are not as much in the common realm of what one studies as part of intro probability courses, these are also relatively misunderstood or underunderstood class of distributions. Okay, like for example, this quote that I think some of you guys have seen. Okay, so in most fields, these heavy tails come up as either mysterious, then surprising. How could it be that this particular phenomena is heavy tailed? Sometimes controversial because it turns out that standard statistical techniques, when applied blindly to heavy tails because of the extreme variability, can lead to erroneous and sometimes flat out wrong conclusions. Like this is one example. This was a very celebrated paper back from the 2000 odd time, where this paper claimed, based on some measurements, that the internet topology, the degree distribution of the internet, was actually power law or heavy tail. I'll define what this means in a bit, and this paper was very widely cited and so on. But then subsequently, it was learned over time that it was the heavy tail conclusion that these guys had reported was a result of some bias that was built into the very measurement mechanism that they were using in order to collect this degree information about it. Right? So it was basically an artifact of the measurement mechanism rather than something that was actually fundamental about the network itself. Right? And these kind of stories are actually there not just in the internet space, but in various other spaces as well. Right? So what we are going to do is talk about, this tutorial will have 3 parts. So we'll talk about properties of heavy tails. What are heavy tail distributions? What are various classes of heavy tail distributions? What are their properties? And so on. Emergence. So what are mechanisms that explain the emergence of heavy tail distributions in various applications? And finally, identification. We talk about estimation. How to do, I will only be able to provide a glimpse on this, but we will talk about how to estimate parameters when one is working with heavy tail data. Okay, so what is a heavy tail distribution? That's a wordy definition. I will write it formally on the board. So at a very intuitive level, as we will see, heavy tail distributions are distributions that are characterized by extreme variability. These are highly variable distributions. Mathematically, heavy tail distributions are distributions with a tail that is quote unquote heavier than that of an exponential distribution. Okay, so what do I mean by tail? So the red curve here is an exponential tail, the blue curve here is a different distribution, and you can see that far out, right? The probability associated with large values under the blue distribution exceeds that under the exponential red distribution, and that is essentially what we will define heavy tails by. So formally, heavy tails are defined as follows. So a random variable, no, RV will actually stand for something else in this talk. So let's spell this out. Random variable X is heavy tailed if the following is true. Okay, so let's stare at this definition in parse. So a random variable is heavy tailed if the following property is true. You take the lim sup of the ratio of the CCDF, the complementary cumulative distribution function. I will also often refer to this as the tail distribution function of f, which is 1 minus the CDF of the random x. The ratio of the tail distribution of function of x to that of an exponential distribution with parameter nu. This lim sup is infinity, and this lim sup is infinity for every positive nu. In other words, this ratio has a limit that is infinity for any exponential distribution, right? So what that means is that the probability that x takes large values is considerably more than that associated with any exponential distribution, right? So that is more formally what it means for the tail to be heavier than exponential. Okay. So if x is not heavy tailed, we'll call it light tailed. So x is light tailed if it is not tailed. And an immediate consequence of this definition, which I'm actually not going to prove, but I would encourage particularly all the students in the audience to try and prove, it's an instructive exercise to go through, and that's the following. So x is heavy tailed if and only if the following is true. Another way of writing this definition would have been to say that if you look at the exponential moments e raised to theta x, this is infinity for all theta greater than 0. Okay. Yes?
Are you only considering non-negative random variable?
At this point, not necessarily. So there's nothing in. So I'll come to that. Later, when we define subclasses of heavy tails, I will sometimes assume non-negativity. Here, I don't worry about non-negativity. That said, this definition of heavy tails applies, naturally to the right tail of the distribution. If you have a two-sided distribution, you may also worry about the left tail of the distribution, which you can symmetrically define as heavy tail by just flipping it over, right? So x would be heavy tail to the left if minus x is heavy tail to the right. So it suffices to only work with the right tail and call it heavy or light. Okay.
Another question.
Yes.
There is another long tail.
I'm going to define long tail. Yeah. So x is heavy tail if and only if. So the fact that your tail is quote unquote heavier than exponential, or it decays slower than an exponential, consequently means that if you look at exponential movements of that particular random variable, they are necessarily going to be infinite for all positive theta. A direct consequence of this is that for those of you who have studied the Chernoff bound and are aware of Chernoff's type concentration inequalities and so on, none of that is going to work here because your moment generating function is infinite for all positive. Okay, so you need different ways when you're dealing with concentration associated with heavy tails. That's just a side remark for those of you who have worked with Chernoff type concentration. Yeah, one final remark I'll make is that even though I have said that the random variable x is heavy-tailed if such and such condition holds, what we are really saying is that the distribution of x is heavy-tailed, right? This is a distribution property, not really a random variable property, but we'll abuse notation and interchangeably say that the distribution is heavy-tailed or the random variable is heavy-tailed. Okay, so let me go through a few examples of, yes?
So it's a integrating function. Right? Can we say that beyond the point are all?
Not necessarily. For certain classes of heavy-tailed distributions, which I will introduce, you will have this property that if you look at polynomial moments, up to a certain point, they are finite and then they become infinity. But this property does not imply that. There are heavy-tailed distributions for whom all polynomial moments are finite. So let's look at the first example. Perhaps the most celebrated example is called the Pareto. Right? This is something that many of you have perhaps encountered. So again, x is Pareto if f bar. So this we have always used f for the distribution function and we use f bar for the CCDF, right? Because the CCDF is what I really care for, as the tail is. So this is given by x divided by xm raised to minus alpha, where xm is greater than 0 alpha. Okay, and in particular, this is the definition of the CCDF for x greater than or equal to xm. Right, so for a Pareto distribution, it has two parameters. There is xm and alpha, both are positive. The support of the distribution is to the right of xm. Okay, and the way to read this is that, of course, there is suitable normalization to ensure it's a well-posed CCDF. But the way to read this is that this is really a power law. The CCDF is decaying as a power law. Right? Something times x raised to minus alpha for alpha positive. That is what a Pareto is. Now, it's very easy to see that a Pareto is heavy-tailed. Right? I don't need to do this. If anybody has a question, ask. Because we know that power laws are going to decay much slower than exponentials. Right? So if you divide a power law by an exponent, the ratio is actually going to go up to infinity. Right? So it's easy to see that these things are heavy-tailed. Right? Coming to the question that was posed below, I just mentioned that in passing here. It turns out that if you look at expectation of x raised to beta or power law moments or polynomial moments of this, there are exact formulae for this which I don't remember, but the thing is going to be finite for beta less than alpha and infinity for beta greater than or equal to alpha. Right? So what that means is that if this alpha were 2, right? This Pareto distribution would have a finite mean but an infinite second moment. If that alpha was 1 or less, it would have an infinite mean. Okay. So historically these distributions have come up. They were, as the name suggests, proposed by Pareto more than a century back. And in fact, the reason for suggesting this distribution is because it seemed to really fit the distribution of wealth. You study the distribution of wealth from an economic standpoint. And we found that these kind of distributions come, right? And when you fit these to a suitable alpha, you end up with conclusions like, the top 1% has 80% of the wealth and something. That those things come. Yes.
To explain why you should get that distribution.
Pareto doesn't, but yeah, there are other people who have looked at mechanisms. Right, there's a rich becomes richer type phenomena, right? Yeah, so one final remark I will make about the Pareto is the following, right? If you look at the CCDF of the Pareto, so the CCDF itself is not particularly, if you look at it in the raw form, then it's of course going to look like this, right? But visually, this picture doesn't really tell you anything about how quickly it's going to 0 or not, right? So the informative way of looking at the scale of the CCDF of the Pareto is on a log scale, right? So if you take the log of the CCDF, note that the log of the CCDF is going to be minus alpha times the log of x. So if the same CCDF is plotted on a log scale, where both the x-axis and the y-axis are plotted logarithmically, then what would it look like? It would look like a linear. Well, yeah, this is not 0. Okay, so yeah. So when I take logs, everything will be negative, but it's going to be 0. with a slope of minus alpha. Okay. So another way to think about Pareto is power law on the CCDF on a log scale, it decays linearly, right? Whereas if you look at, I encourage you to do this. If you look at something like an exponential or a Gaussian, these are examples of light tail distributions. In those cases, you'll see that the CCDF kind of lights down much faster. Okay. So that is all I had to say about the first example, i.e. the Pareto. I hope it's clear to everybody that the Pareto is in fact a heavy tail distribution. The other, perhaps, celebrated definition example of a heavy tail distribution is the Weibull. So the second example I have is the Weibull. Again, I'm going to define this via the CCDF. Okay. So in this case, the Weibull distribution is defined by a CCDF of the form e raised to minus. I'll use a So e raised to minus. This is much better. Beta x raised to alpha. Okay, where these two parameters alpha and beta are positive, and the support is x greater than equal to. Okay, so make sure this is clear. Okay, now is the Weibull heavy tail? If alpha is less than 1, indeed. So if you look at the exponent here, alpha is equal to 1. What is inside e raised to minus is of course growing linearly, right? That's just exponential. If it grows slower than linearly, that's going to cause the tail to decay slower, and therefore the tail would be heavier. Right? Again, it's very easy to go back and check with the definition that that's the case. Whereas if alpha is 1 or more, this would be a light tail distribution because the tail is actually decaying exponentially or faster than exponentially. Right? So the Weibull is this nice parametric family where depending on how I set the parameter alpha, I can kind of transition between heavy and light tail. Okay. So in this case, you will see that F is heavy tail if and only if alpha is between 0 and 1, and light tail if and only if alpha is 0. Okay. And coming back to this question that was asked earlier, if you look at the Weibull, right, one can actually check that polynomial moments of the form x raised to beta are always going to be finite. Oh, yeah, I should use beta, something else. Gamma are finite for all gamma greater than 0. Right? So in the case of the Weibull, unlike in the case of the Pareto, where if you look at these polynomial moments, up to a certain point they are finite and then they become infinite. That's no longer the case when it comes to the Weibull. Weibull is heavy tail, but all these moments are finite. Okay. Let me give you a final and third example. The third example is the log normal. Okay. What is log normal? So x is log normal with parameter mu sigma square if and only if log of x is normal with parameter mu and sigma square. Okay, so that's the definition of a log normal. So please be careful in reading what this name means. Log normal does not mean log of normal. Means take log to get normal. Okay, that is what log normal means. And so another way of seeing it is that in the case of the log normal, you are exponentiating a Gaussian distribution. Right? So in this case, the support is of course going to be non-negative reals. Right? And this, again, I leave it to you to check. If you have a sense of how the Gaussian tail decays, you are now doing an exponential transformation on that tail. It's not too difficult to convince yourself that that is going to result in this being a distribution. Okay, and like the Weibull, all polynomial moments of the log normal are also finite. Okay, so that's the definition of log normal, and yeah, those are the basic definitions of heavy tail and examples so far. Is everybody with me? Any questions on what we've done? Please.
Why is it compared with exponential distribution?
That's a good question. So it just so happens that that boundary, exponential and heavier, leads to a fundamentally different class of distributions which have a a uniformly interesting class of properties and so on. It just so happens that drawing the boundary here leads to an interesting class with nice properties. That's the only, it's a post facto justification. I don't have a fundamental reason why it should have been here a priori.
Is there another boundary at all?
There is, like, well, if you
false in or something.
yeah. So I mean, there are, from in the statistics literature, people talk about sub-Gaussian versus sub-exponential and stuff like that. There is a boundary in that it changes the nature of concentration inequalities that you get when you're estimating means, for example, and so on. There is a boundary. I don't think that boundary is as interesting as this boundary. Okay. So with that, I'm now going to move on to properties of heavy tail distribution. So far, I've only given you a definition, right? I've given you a few examples, but there isn't, so that definition, other than the fact that it means heavier than exponential, what does that mean from some sort of an intuitive standpoint, or what kind of properties does that imply? That is not clear yet. So I'm going to skip ahead and talk about three properties of heavy tail distribution. The first of these properties is called scale invariance. Right? I mean, scale invariance is something that looks good when you have pictures like this, like where you've seen pictures of this. Right? These are like fractals, where as you zoom in, the shape or the figure looks identical, right? As whether you zoom in or zoom out, right? So we will talk about scale invariance in the context of distributions, right? And we will see that a certain variant of scale invariance actually corresponds to an important class of heavy tail distributions. Okay, I think I have some of these definitions here. I can just grab. So first, what does it mean to say that a distribution is scale invariant? A distribution f is scale invariant if there exists some x naught positive and a g. This g has to be a positive continuous function. Yeah, that's such that if you look at f bar of lambda x, so if you are now scaling on the x-axis, the CCDF, that basically gives you some scaled version of the original CCDF, where the scale factor is g of lambda. Okay, so if this can be done, so long as lambda x and x are greater than x naught. X naught is a threshold, right? So long as your pre-scaling and post-scaling points are to the right of x naught, the CCDF should scale in this manner. That the scaled version of the CCDF is some scalar multiple of the unscaled version of the CCDF. Okay, if the CCDF has this property, then we say that the CCDF is scale invariant. Okay.
Ask for G.
Huh?
What do you ask from G?
At this point, G has to be a positive. It just has to be a positive continuous function. It turns out that the only G's that could possibly support this have a very special structure that will come out. Okay, so you can really think of, as I mentioned, this is like a change of scale, right? Whether you're measuring money in rupees or dollars, up to a scale and up to a multiplicative scale, the CCDF should look the same. Okay. Yeah. So you can immediately see that the Pareto distribution satisfies the scale invariance property, right? Because if you replace x raised to minus alpha with some lambda times x raised to minus alpha, it's again lambda raised to minus alpha times x raised to minus alpha. That also tells you what G has to be. G has to be of the form lambda raised to minus alpha. Right? So this is an obvious example. It turns out that a distribution is scale invariant if and only if it is Pareto. Now, this is not very precise. What the formal statement is that a distribution is scale invariant if and only if there is a certain point x naught beyond which the CCDF is something of the form c times x raised to minus alpha. Okay, so it has to be after a certain point, it has to be an exact power law, where by power law I mean some constant times x raised to minus alpha. Then and only then is a distribution scale invariant. So you can see that scale invariance is a very it's a very stringent property, right? Nothing that deviates from an exact power law. It allows the power law to begin after a certain point, but other than that, after that point, you have to have an exact power law. Then and only then can you possibly get scale invariance. Okay. So what I will perhaps do is Yeah, skip the proof of this for now, and I'll come back to it later if there is interest. So as I mentioned, scale invariance by itself is very restrictive because you need exact power law beyond a certain point, right? So that motivates you to look at something that's, so another thing to note is, what does exact power law mean? Exact power law means beyond a certain point, the log, on a log scale, the CCDF has to go down linearly exactly, okay? But that is usually not how real world distributions tend to be. Real world distributions, if you look at their, if you look at empirical CCDFs and so on, you see some sort of linearity, but you kind of have this linearity being approached in some asymptotic sense, right? So the Pareto is too strong, or Pareto exact power laws are too strong to be able to fit these kind of things. So that motivates you to look at asymptotic scale invariance. Now, what is asymptotic scale invariance? Asymptotic scale invariance is f is asymptotically scale invariant if, it's a definition. So if and only if there exists a continuous positive g such that f bar x divided by f bar lambda x divided by f bar x, take the limit of this as x tends to infinity, then you should get g of lambda. In other words, you are asking for something quite similar to what you had before, except you are expecting that to hold only in an asymptotic equivalent sense as x tends to infinity. Which means you are looking for scale invariance only far out into the tail in the limit as x tends to infinity, rather than hold exactly in the prelimit, right? So that is what this is. Because this is notation I'm going to use all the time, let me introduce this. So we will often say that f of t tilde g of t, right, to mean asymptotic equivalence between the functions f and g, right? And typically the asymptote will be clear from the context. Typically it will be t tending to infinity. So what this will mean is that limit as t tends to infinity, f of t by g of t is 1. Okay. So in this context, what does asymptotic scale invariance mean? F is asymptotically scale invariant if and only if f bar of lambda x is asymptotically equivalent to g of lambda and z bar x. When you see it like this, you can see that what we have done is basically replaced an exact inequality with an asymptotic equivalent. That is basically what asymptotic scale invariance means. Now, when it comes to scale invariance, we know that the only distributions that have scale invariance are pure Paretos, right? Or at least something that's multiplicatively like a Pareto beyond a certain point. So what is the class of distributions that gives you asymptotic scale invariance? That class of distributions is corresponds to what is called the class of regularly varying distributions. Okay, so this is a class of distributions that generalizes the Pareto and corresponds exactly to the class of distributions that actually satisfies this asymptotic scale invariance property. Right? So rather than use that definition, I'm going to use a slightly different definition to build it a little more clearly. That's the following. So we say that f is regularly varying with index minus alpha. So this is going to be denoted by f belongs to Rb minus alpha. Right, so throughout this tutorial, Rb is not a random variable, Rb is regular variation. Okay. For alpha greater than equal to 0, if the following is true. Limit x tends to infinity, bar of x lambda upon f bar x is equal to lambda raised to minus. Okay, so this definition looks similar to the definition of asymptotic scale invariance, except that I've given you a very explicit structure for G. Okay, but it turns out, as I alluded to before, that in these kind of things, the only possible form that G could have is in fact of this form. That G has to be of the form lambda raised to minus alpha. So it turns out that the class of regularly varying distributions as defined here is exactly matching to the class of asymptotic scale invariant distributions that are defined there. Okay, So asymptotic scale invariance generalizes the notion of scale invariance from an exact property on the distribution body to an asymptotic property on the distribution tail. And that in turn, the class of distributions that satisfy that property then expands from the class of what I would call pure power laws to the class of regularly varying distributions. Okay, so that is now the first class of distributions that we will study. Okay, so yeah, this is implicit in what I just said, that f is regularly varying with index rather f is regularly varying is equivalent to saying that f is asymptotically scale invariant. Okay, so asymptotic scale invariance is exactly regular variation. Okay. Okay. Yeah. So now what I'm going to do is build, maybe for the next 20 minutes or so, some properties of regular variation, and then we will see how, even pictorially, regularly varying distributions generalize the class of pure power laws. Okay. So the first thing I need to do is define a slowly varying distribution. Sorry, slowly varying function. A function L from the non-negative reals to the non-negative reals is slowly varying if L of lambda x asymptotically L of x for all lambda greater. Okay, another way of writing this would have been to say that the ratio as x tends to infinity of L of lambda x divided by L of x is equal to 1. Okay, a function that satisfies this property is said to be slowly varying, right? Can somebody give me examples of slowly varying functions? Some examples are trivial, but students in particular. Yes, any function that's a constant is obviously regular, slowly varying. Any function that approaches a constant limit also is, if L as x tends to infinity converges to C, where C is any constant, obviously that would be slowly varying. Anything else? The exponential is actually not at all. That's a good thing to try. If you look at something like e raised to, doesn't matter whether you're looking at a growing exponent or a decaying exponent. E raised to lambda x divided by e raised to x, right? This is either going to go off to infinity or go down to 0. It's not going to approach 1. An exponential is very, in an exponential distribution, if you change, see what this means is that if you change units, asymptotically the function looks identical. Polynomials are also not. So if you take, for example, x square, does x square satisfy this property? No. But you get lambda square x square and they're not equivalent. Yes, logarithms. So things that are, functions that are slower than power law will work. So for example, logarithm will be slowly varying. Polylogarithms like log square x, 1 by log x. So polylog functions, these are all slowly varying. Okay. Note that slow variation is in fact identical to the condition that we had for regular variation, except that alpha is 0. Right? So corresponding, so in some sense, the class of functions that satisfy this property corresponding to alpha equals 0 is exactly what I'm referring to as slowly varying functions. Okay, and as I mentioned, examples are functions that either approach a limit, identically constant, logs, polylogs, and so on. Okay. So here is a lemma that describes how these slowly varying functions work. So for slowly varying L, the following is true. Limit x tends to infinity, x raised to rho times L of x is going to be 0 for rho less than 0, infinity for rho greater than 0. Okay, so if you take a slowly varying function and multiply it by a polynomial, the polynomial will essentially dominate so far as asymptotic behavior is concerned. Rho is positive, then x raised to rho blows up, and so will x raised to rho times log, polylog, any slowly varying function. Similarly, when rho is negative, the x raised to rho will decay to 0, and so will that. Whether you multiply x raised to minus 2 with log or log square or log raised to 100, the limit is still 1. Okay. This is actually not that easy to prove. It's not immediate from this definition that this holds. It takes some work to actually come here. So I'm not going to get into the proof of this. I will allude to this and point you to where it comes from later. But this takes, this is not immediate. But once you have this, we can say something interesting about regularly varying distributions. So the first thing I'm going to mention is that f is regularly varying with index minus alpha. Remember, this alpha has to be greater than 0, right? X raised to minus alpha, because it's a tail, it's a CCDF, it has to go down, right? So alpha has to be greater than or equal to 0. Okay?
That limit has to do with regular. That is only for functions with slowly varying.
Yeah, I'm going to make the connection between regularly varying distributions and slowly varying functions just now. Yeah. So f is regularly varying with index minus alpha if and only if f bar of x is x raised to minus alpha times L of x, where L is slowly varying. Okay, so this is the connection. So regularly varying distributions, remember regularly varying distributions are exactly those distributions that satisfy the asymptotic scaling variance property. Those distributions are necessarily of the form, if it is regularly varying with index minus alpha, then the CCDF is going to be x raised to minus alpha times a slowly varying function. Okay, so again you can see the connection. Exact scaling variance requires a strict power law. Asymptotic scaling variance requires a power law multiplied by a slowly varying function. Where a slowly varying function is one which, as the name suggests, is slowly varying asymptotic. It doesn't change too fast as you go further and further up to the right. Okay, so this is actually quite easy to show. Like if you have a CCDF of this kind, you just have to blindly apply the the definition of slowly varying to argue that if the CCDF has this form, then it is regularly varying with index minus alpha. If you have a function which is regularly varying, I'll just mention this. So for the forward implication, so suppose f were regularly varying with index minus alpha, you just define L of x as f bar of x divided by x raised to minus alpha, and show that this L is slowly varying. Again, just have to apply the definition of all of this. Look at L of lambda x divided by L of x, take the limit as x tends to infinity, you will get 1. Okay, so this is how you would show this. This gives you a representation theorem. There are better and more precise representation theorems for regularly varying distribution, but this is something that's informative. That regularly varying distributions are those which are power laws multiplied by a slowly varying function. Okay, now where is the connection to heavy tails in all of this? The connection to heavy tails comes here. So the class of regularly varying distributions is a subset of the class of heavy tail distributions. Okay, so all regularly varying distributions are heavy tail, right? So Pareto is anyway heavy tail. We now have a generalization of the Pareto, right? We have gone from scaling variance to asymptotic scaling variance. That superset that we have constructed called regularly varying distributions is also heavy tail. Okay, to show this is actually very straightforward. All you do is, so suppose that f is regularly varying with index minus alpha, then you look at f bar of x divided by e raised to minus mu x, right? The exponential CCDF. So what is this? This is e raised to mu x times x raised to minus alpha L of x. Okay, you have to argue that this thing goes off to infinity. Okay, the way I would do this is to say that this can be written now as x raised to epsilon times L of x, where epsilon is some positive constant, right? Times e raised to mu x times e raised to, sorry, x raised to minus right, all I've done is multiplied by x raised to minus x raised to epsilon and divided by x raised to epsilon. Okay. Now this thing, because epsilon is positive, goes out to infinity by virtue of that property that I've written there. That second piece anyway goes out to infinity because you are multiplying some decaying power law with a growing exponent. Right? So this thing will go out to infinity. So that shows that all regularly varying distributions are there. Okay. Okay, so I'm going to more or less conclude here, but I do want to mention a few other interesting properties. So there's an entire chapter in the book for those of you who are interested. There's a free preprint that's available online, so if anybody wants to download. So there are lots of very interesting properties that regularly varying distributions have. One very interesting one being that there are certain things that are easy to do with power laws. Right? If you have something that's exact Pareto, integrating power laws is easy. We know how to do that from our high school days. Differentiating power laws is easy. Right? So for example, going from the CCDF to the density function, all of that is easy. It turns out that all those quote-unquote nice properties also extend to regularly varying distributions, except that those properties hold asymptotically rather than exactly. Right? So long as you are working with asymptotic properties, you can do many things that you would do with exact power laws, also with the power laws multiplied by these slowly varying functions. Okay, so that's the power here. I'm not going to, I won't have the time to get into any details in this, but I'm going to state one result which I think highlights this idea at least. So suppose that alpha is greater than 1 and define f of x to be x raised to minus alpha. So exact power law. Okay. So now, what is the integral from x to infinity of f of t dt? Okay, we have all done this. So you guys are going to be faster than me at this. This thing can easily see. You're going to get x raised to minus of alpha minus 1, right, divided by alpha minus 1. So I'm going to write that as x times f of x upon alpha minus 1. Okay, so this is what you get when you. So this is the kind of thing that you would do if you were integrating the tail, right, of a density function, for example. Okay, so if you have a power law, then this is what happens. Now suppose that f of x is of the form x raised to minus alpha times L of x, where L of x is slowly varying. In that case, it turns out that integral x to infinity f of t dt will of course not have an exact representation of this kind, but as x becomes large, so now asymptotically equivalent to x times x upon. Okay, so as I said, this nice integration property gets preserved, except that instead of an exact statement, you have an asymptotic type statement. Which, if you think about it, is pretty remarkable, right? Because when you are integrating this, there is a slowly varying function sitting inside. So for this to hold, it's as though that slowly varying function kind of nicely popped out of the integral, right? For this kind of stuff. But so this is part of a broader class of results called Karamata's integration theorem. That is just Karamata's theorem. There are similar versions for what happens if you are integrating if alpha takes other values, except the range that I talked about. There are versions of this with differentiation as well. You know, the way you differentiate power laws, what happens when you asymptotically differentiate regularly varying distributions. So there's a very broad class of powerful things that you can say about regularly varying functions more generally, which let you generalize, right? Things that you would have done with exact power laws, asymptotically you can do that with regular range. Yes.
The strong implication of the work, like integration of the expansion. Important application.
Yeah. I will give you an application of this as an example. 5 minutes from now. Yeah.
So this is can be shown using logical rule.
No. Right? No, this is a deep result. Takes work.
And take a ratio and take a derivative of the numerator.
No. Okay. One final result I will mention. Yeah, this also will be unfortunately without proof, but yes.
Which part is it? Left?
The left. Left is trivial.
Left.
It's the right. That how to play with the slowly varying function and how to pull that out. Because note that
Irrespective of L of x.
because the same L of x is showing up here, right? Because f includes the L. So it's not like there is a different L here or something. It's not. That would have been a weaker result. It's the same L, right? That's showing up. Okay, so final result I will mention is that f is regularly varying with index minus alpha. It implies the following. It implies that limit x tends to infinity, log of f bar x upon log x equal to minus alpha. Can somebody interpret, any of the students, can they interpret this result? If f is regularly varying with index minus alpha, then limit as x tends to infinity of log of f bar x by log x goes to minus alpha. This again is a generalization of a statement I mentioned about the Pareto that when we were discussing that. So it's not exactly linear. It's nicely, many of these properties now become asymptotic properties. So log of f bar is no longer decaying linearly, but asymptotically it decays linearly with an asymptotic slope which corresponds to the index of the power. Okay, so you don't get a straight line, you get something that asymptotically approaches a straight line with the slope of minus alpha. Okay, so that's another nice property of regular variation. This is in fact also abused when it comes to statistics, because when people want to do estimation of this alpha parameter, what they will often do is just take the empirical CCDF, and again it's only asymptotically getting there, right? So you have to be careful. So then they'll probably eyeball a region beyond which it kind of looks linear, and then you fit a regression line onto that and estimate the slope, and it turns out that's a statistically unsound way of estimating this index. So that's something that we talk about towards the end. Yes. No. It turns out that this is a one-sided thing. So this becomes a little loose. So it is clear that if f bar satisfies this property, it's clearly heavy-tailed, because asymptotically the log of it is decaying as minus alpha times log x. But you can construct, you have to work to construct these things. So they're not like the most of the distributions that you hook up which satisfy this property will also be regularly varying. But you can construct distributions which satisfy this but are not regularly varying. So this defines a broader class of heavy-tailed distributions that goes beyond regular variation. But this class by itself doesn't have too many interesting properties, so I am not aware of a name that's been given to this class. But regular variation is a subset of this. All right. So let's conclude with a few examples of regularly varying distributions. So the Pareto is an obvious example, but there are a few more interesting examples of regular variation which you may have encountered in the past.
So by the way,
Yeah.
this, you had a result saying that regular varying is a subset of heavy tail.
Yeah.
This is basically that. This result is it?
No. So this is a superset of regular variation still within the class of heavy tail distribution. Like yeah. Because the implication goes this way. Regular variation implies that you satisfy this property. That the log of the CCDF is asymptotically log x times something, right? That's a superset of regular variation, but still heavy tail. It's easy to show that that's heavy tail, but it's not necessarily regular variation.
So does the theorem apply to this class?
Not to my knowledge. You need, there is a rich class of things that you can do exploiting the regular variation property. So you need that, to the best of my knowledge. I'm not aware of a generalization. Okay. So examples of regular variation. The first of these is called the Burr. Okay, so the Burr distribution looks as follows. So f bar of x is equal to 1 plus lambda x raised to minus c or minus k. Right? Where the parameters c lambda, 1 plus lambda x raised to, c lambda k are all positive. Yeah, and x is greater than or equal to 0. Okay. So, for example, if lambda is 1 and c is 1, this looks like 1 plus x raised to minus k. It's basically, you can think of it as, so Pareto is sharp, right? There's no density up to xm, and then your power law begins right away. This is a bit more gradual because the support is from 0 to infinity rather than from Higgs threshold. But yeah, so this class of distributions is called Burr. Okay. So is this regularly varying? Yes, it's very easy to see this because f bar of x, note once you have this structure, it's easy to see that this is asymptotically just lambda raised to k, x raised to minus c times k. Okay? Right? Because if you divide this by this, the limit as x tends to infinity will be 1. Right? And right from here, you can read off that it is regularly varying. Right? Because whatever, once you have a tilde, you can write that with an equality with a slowly varying function patched together with a slowly varying function converging to 1. Right? So asymptotic equivalence is sufficient. So this automatically implies that f is regularly varying with index minus c times k. Okay? So the Burr distribution is regularly varying. The second example is something that we are all familiar with. It's called the Cauchy. Right? The Cauchy is something that typically you study as part of intro probability as an example of a distribution for which the first moment is undefined. Right? So in this case, the density function looks as follows. Right? I'm going to do this for the standard Cauchy. There are scaled versions of this that you can write, which is 1 by pi times 1 by 1 plus x squared. Okay. I don't know if I got the pre-factor right, but that you can check. Okay. Now, can somebody tell me, in light of what we have talked about, whether and if so, why the Cauchy is heavy-weight, or why is it regularly varying? So I have defined, unlike all the other distributions that I've defined so far, those were defined directly in terms of the CCDF. Now I've defined, because the CCDF of the Cauchy will have some tan inverse or something, right? So I don't want to write that. So it's cleaner to just write the density function. From the density function, can I conclude something about the CCDF, which in turn allows me to, so this basically goes back to, I don't know who, I think, Rahul, one of you guys asked, where can you put that integration property to use? Well, integrating the density function from x to infinity is going to give you the CCDF, right? So right here, you can see that f of x is asymptotically, again, I'm going to ignore the 1 by pi, it's just a constant, right? So it's basically of the form c by x squared. Okay, now what does it mean that f is c by x squared? From the integration property, it implies that f bar of x is asymptotically c divided by x, c prime divided by x, right? And so therefore, the Cauchy is in fact regularly varying with index minus 1. Okay. So this is just one example of where those integration properties come to No, this is an if and only if. Yeah, it goes both ways. Thanks, that's a good point. Absolutely. So, in fact, that answers the question I think that Chandramani was asking. So, the regularly varying functions are exactly the functions where that asymptotic equivalence goes. That's true. So, it does not hold for any broader class. Okay, so one final example I have, and that is the Frechet. The Frechet is something that we will talk about later in the tutorial as well when we talk about extreme value theory. So I'll just write it here. This is a bit interesting because here the power law is not necessarily staring you in the face when the definition is written. Right? So the Frechet is defined. I'm going to define it via the CDF rather than the CCDF. The CDF is given by e raised to minus beta times x minus xm whole raised to minus alpha. Again, so this beta, xm, these are the irrelevant terms. So these are the uninteresting parameters. This is just scaling your currency and calculating the distribution. The interesting parameter is the alpha. Okay. Yeah. So I claim that this is regularly varying. The what index can can somebody tell me why this is regularly varying? So note that this is the CDF, not the CCDF. The CDF should of course tend to 1 as x tends to infinity. It should, right? So it's e raised to minus something, where that something goes off to 0. Right? So we are looking at e raised to minus something where that something goes to 0. So the asymptotic information that I seek can be obtained by just doing a first order Taylor expansion of e raised to minus x around x is equal to 0. Okay? So in that case, you will see that this is just 1 minus, well, beta times x minus xm raised to minus alpha plus little o of the same thing, x minus xm raised to minus alpha. Remember, x minus xm raised to minus alpha is going to 0. That's a lower order term, right? That's the residue from your first order expansion. So then in that case, you can see that f bar of x, which is 1 minus f of x, is basically beta times x minus xm raised to minus alpha plus little o, right? Which is asymptotically simply beta times x raised to minus alpha, right? So again, I don't care about characterizing what exactly the slowly varying function is. There are some slowly varying functions such as this thing represent, right? And so that shows that the Frechet is in fact regularly varying with index minus alpha. Okay, so those are that is what I had to say about regular variation. So here is the picture that we have so far. So we define heavy tail distributions based on this property of the tail being heavier than exponential, right? That by itself, there were a few examples that we were able to put, but that by itself doesn't tell you a whole lot, right? And next we define the scale invariance type property and generalized it to asymptotic scale invariance that defines regular variation. So far we have heavy tail distributions, a class of heavy tail distributions called regularly varying distributions. This class includes not just Pareto but all the others that we wrote, the Burr and so on, right? And it turns out that you also have the heavy-tailed Weibull and let's say the log normal that are outside of this class. Okay, I haven't justified these two claims yet, but I've defined both of these things. So I leave it to you to check. Go back and look at, for example, the Weibull is perhaps the easiest one to do. Show that the Weibull couldn't possibly be expressed as x raised to minus alpha times a slowly varying function. Right? You cannot do this for a slowly varying function. That's the point, right? Because the way in which it scales is very different from that of power law. That's the point. Same thing with the log number. Okay? So these are examples of heavy tail distributions which are not regularly varying. Okay? And one thing that I just mentioned without writing out the details is that the property that I mentioned about the Pareto, namely that the moments up to alpha are finite and beyond alpha are infinite, that property is in fact inherited by the entire class of regularly varying distributions. All regularly varying distributions will, if they are regularly varying with index minus alpha, then x raised to moments, right, which are up to alpha, less than alpha are going to be finite, beyond alpha are going to be infinite. At alpha, you can either be finite or infinite. Right? Unlike in the case of a Pareto, you know that the alpha moment of the Pareto is guaranteed to be infinite. Here, depending on whether the slowly varying function is like log x or 1 by log x or something of that sort, at that boundary, you can basically construct examples where the alpha moment is either finite or infinite. But the broad property still holds. Okay, so I'm going to stop this property here. Any questions on regular variation? Anybody? Okay. So that is the first of the three properties that I wanted to talk about. The second, interesting property. Yes.
So usually, so I come from magnets, so somewhat there. We generally define heavy as something which has a finite higher moment kind of loop things. How does that tie into this class? You said Taraka has a finite higher moment. But,
I don't know. So
is the reverse? Can you characterize this?
Not to my knowledge. No.
Not that.
No. I think regular variation satisfies the property that up to a certain point your moments are finite, polynomial moments are finite, and then they become infinite. I do not believe that that the converse is true. Yeah. So it's not. Let's just say that that's not a clean class.
It's clean up or estimation.
You can bound certain things, by knowing that a certain moment is upper bounded by something. That's true.
Yeah.
But I don't think it has. Yeah. That class does not coincide with regular variation. Okay. Now the second property, the second defining property I'm going to talk about is called the catastrophe principle. Okay, so I have something in the slides that I can run through here quickly. Yeah, so here is a thought experiment. Okay, so I assume there are 50 of you in the room. So suppose I take a poll, right, and then I measure all your heights and so on, and it turns out that the sum of the heights of the so the sum of the heights ended up being, let's say, 300 feet, and I also polled how many. Let's assume all of you are on Twitter. I also asked you how many Twitter followers you are, and in both cases, the sum ended up being higher than what I would expect. Okay. So, for example, the sum of the heights was, let's say, close to 300 feet. That means, on average, everybody is a 6-footer in this room, which is an extremely unlikely occurrence, right? I mean, the sum of the number of Twitter followers is some million plus. That is also a somewhat unlikely occurrence, right? And you might ask yourself, a natural question to ask is, what explains this unusual occurrence, right? How has this rare event come to be, right? And it turns out that the most likely manner in which these two things could have occurred are fundamentally different, right? So if the sum of the heights was about 300 feet, it most likely is because there just happened to be a bunch of taller than average people in the room, right? Some visiting basketball team and ISC's basketball team, all of them happen to be taking a heavy tails workshop or something like that, right? That's the more likely thing, right? Many people had to contribute to making the sum larger than what you might expect. But when you look at something like Twitter followers, the most likely reason why the sum of Twitter followers is like a million plus is most likely because one of you in the room happens to be some god Twitter, celebrity of some sort, right? Contributing practically the entire sum just all by yourself. Same is true of money. If the sum of the net worths of everybody in this room exceeded $1 billion, it's most likely because one billionaire happened to be in the room. Right? It's very unlikely that it will be because a lot of us are individually rich but not that rich. Right? So that is the qualitative difference between the explanation for how this sum ended up being large. So this we refer to as a conspiracy principle, right? Because multiple factors had to quote unquote conspire to make the sum large. That we refer to as a catastrophe principle. That's the word comes from bad things happening. I don't think Twitter followers being large is a bad thing, but catastrophe in the sense that one catastrophe resulted in the unexpectedly large sum. Okay. So this is actually a property that is broadly true of a wide class of heavy tail distributions. So this is just a nice illustration of this. So suppose that x1 and x2 are IID Weibull. Okay, IID Weibull. Remember, depending on how I choose the scale, that alpha parameter for the Weibull, I can get both heavy tailed and light tailed, right? Now, given conditioned on x1 plus x2 equals d, where think of d to be something that is significantly larger than twice the mean of these random variables. Right? So it's an unexpectedly large value of the sum. Conditioned on this, what is the marginal density of x1? Right? D is large. So I mean, I'm going to show you a numerical experiment. In this case, D was I think each of them were unit mean and D was 10. right? So what condition on this? This is a numerical calculation that all of you can do, right? You know, you can convolve and figure out what the joint density is. The condition on this, see what happens. So you see something quite interesting, that if alpha were greater than 1, that's the light-tailed case, the conditional density of x1 is this blue curve, blue, violet, whatever curve here, right? So you can see that the density peaks in the middle. What does that mean? That most likely reason, the most likely manner in which the sum was large is that both of these random variables contributed roughly equally to the sum, right? So that's what is indicated by the fact that the thing peaks here. In the case of the exponential, alpha equals 1. If alpha is 1, a variable is just plain exponential. Then from the memorylessness property of the exponential, you should be able to convince yourself that the marginal density of x1 conditioned on x1 plus x2 equals d is just flat. Okay, x1 could have contributed uniformly at random any value from 0 to d. So consequently is the case with x2. Interestingly, when you look at the heavy-tailed case, you see that the density has two peaks, one peak way on the left and the other peak way on the right. What does that mean? So if x1 is taking very small values, note that x2 is taking the large value, right? So what is the fact that your marginal density of x1 has these two peaks around 0 and d means that the most likely manner in which x1 plus x2 was large, d, is that one of these guys contributed practically everything, right? So that's now a simple illustration of the catastrophe principle at play, right? So the blue curve is like a conspiracy. Both of them have to conspire to create the large sum. The red one, the heavy tail case, is the catastrophe. One guy is large. Okay. You can actually also formalize this a bit more, which I will do in a bit. The catastrophe principle can be formally stated as follows: that if x1 through xn are IID, random variables, here I need non-negativeness. Somebody was asking about non-negativeness. Here I will talk about non-negativeness for now, because when it comes to sums, I don't want some negative value. So the probability that the max is greater than t is asymptotically the probability that the sum is greater than t. Okay, so maybe it's easier to parse the left-hand side first. The left-hand side is that the probability that the sum of n IID random variables exceeds t, right? T being large, because we are talking about an asymptotically equivalent statement. This is asymptotically equivalent to the probability that the max is greater than t, which means that one guy is contributing to a value greater than t, and that is in fact the manner in which this is happening. Another way of writing that very statement is the following. Okay, write this as a conditional probability. The probability that the max of x1 dot xn is greater than t, conditioned on the sum which approaches 1 as t tends to infinity. This conditional probability is exactly the ratio of the left hand side to the right hand side. Right? So the fact that those two are asymptotically equivalent means that this conditional probability, conditioned on the sum being greater than t, with probability approaching 1, the max is greater than t. Okay? Yes?
Because if max of n ID and I is greater than t,
Sure.
the sum is greater.
So that's the whole point. So the fact that the right hand side probability is greater than the left hand side probability is trivial. But the fact that asymptotically they are the same means that the most likely manner in which the sum is large is that the max is large. So that is called the catastrophe principle. Yes. These are IID. IID non-negative random.
The implication in both the directions. There you show one direction.
No, this is equivalent, right? It's because this is exactly the same as the ratio of the left hand side to the right hand side. Yes, that's just equivalent. Okay. Now, what is the conspiracy principle? The conspiracy principle doesn't have as clear a statement because the manner in which this probability behaves relative to this probability depends on which light-tail distribution we are talking about. But one weak but somewhat general statement that one can write is that the conspiracy principle is where the probability that the max is greater than t is little of the probability that the sum is greater than t. Another way of saying that is that this conditional probability goes to 0. right? Given that the sum is large, the probability that the max is comparable, conditioned on the sum being large, the probability that the max is comparable to the sum goes to 0 as t. When that happens, we can say that there is some sort of a consequence. Not really. I know that this is a weaker way of stating. I'm not telling you that everybody is contributing roughly equally and so on, right? So it's weaker, but at least it is in contrast with what I have. So that's really what we are going to be talking about. Okay? Yes.
In the catastrophic principle, we are saying T asymptotic. But in a practical sense, like how large or what's the smallest T which this?
That depends on the distribution under consideration, right? Yeah. So this T has to be larger than the mean. Right? These are basically, we are talking about two rare events. So, I mean, yeah, you will expect that these two probabilities are close to each other for moderately large values of T. But I'm not aware of a way of like being precise in understanding the rate at which this ratio goes to 1 or something. Nothing universal. You can do that for specific distribution classes, but not generally to mine. Yeah. So this is an asymptotic property. All right. So this class of distributions that is called the catastrophe principle is actually very useful. This defines another class of heavy-tailed distributions called sub-exponential distributions. Many of you have heard of sub-exponential in a different context. There is some abuse of notation that the community has perpetrated, which I will at least clarify. But this class of distributions is called sub-exponential distributions. It's a class of distributions that satisfies the catastrophe principle. Okay, and this catastrophe principle comes up very often in the analysis of random walks, queues with heavy-tailed workloads, and so on. Right? Because when you have heavy-tailed random walks with heavy-tailed increments, you end up with this kind of a thing where the most likely reason for the random walk to have done something unexpected, crossed a certain threshold or something, very likely because of a single big jump, one jump that contributed to the entire deviation that one is seeing. Okay. This class of sub-exponential distributions, so f is sub-exponential. Now here I need f to be non-negative. There is a way of generalizing sub-exponentials to real value distribution, which I'm not going to get into. But for non-negative f is said to be sub-exponential if for IID xi having distribution f, the probability that the sum is greater than t is asymptotically n times the probability that one guy is greater than t. Okay. Now on the surface there is a mild discrepancy here, because when it comes to sub-exponential distribution, the equivalence is with n times the tail of one random variable. In the former case, it's basically this max, right? But it turns out that these two definitions are in fact equivalent. Sub-exponential distributions are exactly the class of distributions that satisfy the catastrophe principle as stated above. Okay. The reason for that is that universally, so long as the distribution has unbounded support, the tail of the max is essentially n times the tail of the individual random. Okay. So this is very broadly. This has nothing to do with heavy tails. This is just a standard property of the max. The max of n IID random variables is going to be greater than t. Probability of that is going to asymptotically be approximately n times the probability that any one guy is greater. Okay, how do you show this? This is actually easy. So probability that max of x1 through xn is greater than t, right? This is equal to, the way you handle this is, of course, everybody has done this. So 1 minus the probability that the max is less than equal to the IID. So this is going to be when 1 minus f bar of t the whole raised to n. Right? This is the probability that one guy is less than equal to t. That raised to n is the probability that everybody is less than equal to t. 1 minus that is the probability. Okay. Now let's look at this one. So this is a binomial expansion. To expand this out, then you will get 1 minus. When 1 minus, one term in this is going to be n times f bar of x, right? And then you have a bunch of terms of the form f bar square, f bar cube, f bar whatever, and so on. Right? All of that is little o of f bar of x. Okay, so what does this mean? That this is basically going to be asymptotically n times f bar of x. Okay, so this is true for any distribution, so long as this f bar is positive for all x. In other words, there is unbounded support to the right. It's always true that the max, heavy tail or light tail, the tail of the max is asymptotically n times the individual tail, right? So therefore, these are two equivalent ways of defining sub-exponential distribution. That the probability that the tail of the sum is asymptotically n times the singular tail, or the tail of the sum is asymptotically the tail of the max. Okay. So this class of distributions is called sub-exponential distributions.
The example.
I'll tell you. Yeah. So it turns out, as you might expect, where did I? So it turns out that the class of sub-exponential distributions, let me call it S, is a subset of, well, put it like this. Regularly varying distributions are a subset of the class of sub-exponential distributions, which in turn are a subset of the class of heavy tail distributions. Okay, so all regularly varying distributions are sub-exponential, all sub-exponential distributions. So I had planned to actually cover proofs of both of these implications, but given that we have 5 minutes, is that 5 minutes to the break, right? What I'm going to do is I'm going to skip the latter one, which is I think less interesting, but because we have talked about regular variation for a while, I think it might be interesting to highlight how one would establish that regularly varying IID random variables will satisfy this catastrophe type. One thing I should mention is that one can also prove that having this property hold for every n greater than equal to 2, it's equivalent to it holding for some n greater than equal to 2. In other words, you don't need to prove this for all n greater than equal to 2. If you prove it for n equals 2, you're done. Okay, that's a non-trivial result, but it can be shown. Yes, both Weibull and log normal are in the class of sub-exponential distributions, but outside the class of regular.
Why is it called sub-exponential here?
Yeah, because see, sub-exponential distributions are heavy tail, so there's poor naming on all sides. See, heavy tail distributions are really, by definition, what are sub-exponential. Why? Because they are decaying slower than exponentials. Hence the name sub-exponential. But we haven't called this class sub-exponential. We are going to class this called sub-exponential, which is a subset of this. But this, this, as we will see in a bit, this, even though this is a strict, inclusion, I mean, only pathological, distributions lie here. So you have to, hook up something really pathological to lie outside of S and inside HT. So for most distributions we care about, S and HT are almost the same. But the word sub-exponential comes really from the defining property of heavy tail, namely that the decay is sub-exponential, slower than exponential.
Yeah,
I know. Yeah, I'll address that. Yeah. So there's almost like serious abuse in the use of this term. Yeah. So let us actually do just one part of it, which is this. Okay. So F is regularly varying with index minus alpha. X1 and X2 are in fact having distribution F. Okay. And I will just do this for n equals 2. Even though you can invoke the result that I said, which tells you that it suffices to do n equals 2, the approach that I'm using for regular variation can directly be applied even for n greater than 2. So the point is that you don't need to use that non-trivial result that I mentioned. You can, using similar ideas, also prove this generally. Right? So what I want to prove is the following. Prove that if I have two IID regularly varying random variables x1 and x2, I want to prove that the probability that x1 plus x2 is greater than t is asymptotically 2 times f bar of t. Okay. Once I prove this, that's really the defining property of the sub-exponential. Now, the way in which these kind of asymptotic equivalences are proved is oftentimes by proving a lower bound and an upper bound. So you come up with a lower bound on this, which asymptotically matches the right hand side. You come up with an upper bound on this, which asymptotically matches the right hand side. Sandwich. So let me first go through the lower bound. So each of these is going to be very quick. So yeah, that's why I'm confident that I will not delay your coffee break. But I think it's instructive to see how the properties of regular variation actually can be applied to see this. Okay, so let's first look at the lower bound. The lower bound is basically based on the following observation, that the event x1 greater than t union x2 greater than equal to t implies the event that x1 plus x2 is greater than. This is obvious, right? We are working with non-negative random variables. Either one of them is greater than t, obviously the sum is greater. So therefore, the probability that x1 plus x2 is greater than t is greater than or equal to the probability of this left hand side. That's now the union of two independent events, right? So therefore, I can apply our standard formula x1 greater than t plus probability x2 greater than t minus the probability of the intersection of those two. But mind you, this is all IID, so this is probability x1 greater than t minus probability x1 greater than t the whole square. Okay. Now note that this lower bound is asymptotically 2 times f bar of t, right? Because twice comes from here, and when you square, you are getting something of a little o of f bar of t. So the lower bound that we have got is asymptotically 2 times f bar. Okay. Now let's look at the upper bound. The upper bound actually follows the following reasoning. Now I need to reverse the order of the implication, right? Because I want common the other side. So I want to say that x1 plus x2 greater than t actually implies some property. What is that property? So that property is the or implies the event the following. So take delta to be between half and 1. You can take to be greater than half. Between half and 1. Okay. So x1 greater than delta t union x2 greater than delta t union x1 and x2 greater than 1 minus delta t. Okay, so I mean, just to make it easy to interpret, let's pretend that delta is 3/4. Okay, what does this mean? That if the sum is greater than t, my claim is that either x1 was greater than 75% of t, or x2 was greater than 75% of t. But if neither of those two held, then both x1 and x2 have to be greater than 25% of t. Right? So that's the idea. So that now gives me an upper bound. So an upper bound is going to be probability x1 plus x2 greater than t can be upper bounded by, well, twice the probability that x1 is greater than delta t plus, now this is union bound, right? Upper bound. So union bound here is going to give me probability that x1 is greater than 1 minus delta t the whole square. Okay. Now if you take this upper bound thing and asymptotically, this thing is asymptotically, I'm being a little sloppy with steps here, I hope you're okay with that. So twice the probability that x1 is greater than delta t. Okay, but you have regular variation, because this term is little o of the first term, right? Because of regular variation, this is just going to be 2 times delta raised to minus alpha probability x1 greater. Right, so I have an asymptotic upper bound, and this upper bound in particular holds for every delta that is greater than half. You can let this delta tend to 1, and that will give you a matching. Okay. So we have used regular variation properties to argue that regularly varying distributions are in fact sub-exponential. Okay. So going back to pre-break, let's just look at the picture of where we stand so far as our understanding of heavy tails is concerned. This is the class of all heavy tails. This now is the class of sub-exponential distributions. This is the class of regularly varying distributions. Regular variation, we give a bunch of examples. The log normal, the y will lie here. Okay, so this inner class satisfies the property of asymptotic scale invariance. This outer class satisfies this catastrophe principle. All of these are subsets of heavy fields, right? Now, I have not told you why it is that log normal and Weibull are in fact sub-exponential. It turns out that's not as easy. So if you just use, so this is what I would call a time domain from an electrical engineering standpoint. This is like a time domain condition, right? You're looking at CCDFs and so on, right? But when it comes to sums of independent random variables, oftentimes transform domain approaches are easier, right? So I mean, these convolutions are often messy. So from first principles, just using convolution of log normals and Weibulls, it's very difficult to show that these are sub-exponential. It turns out that there are sufficient conditions for sub-exponentiality that arise from hazard rate. So you can use, in terms of the hazard rate, there are some conditions, sufficient conditions for sub-exponentiality. And one can prove that the log normal and the Weibull, fortunately they're both continuous random variables with a well-defined hazard rate, they satisfy that hazard rate condition. So that's how one proves it. I'm not going to get into the hazard rate condition, because of shortage of time, but that's the story, right? Now comes to the abuse. The sub-exponentials here are a subset of heavy-tailed distributions, and I said that's practically, even though the inclusion is strict, there are distributions up here, these are pathological, okay? But it turns out that in the statistics community, and now more recently also in the learning community, sub-exponential distributions are used to refer to as the distributions that I refer to as light-tailed. Distributions where a certain exponential, positive exponential moment is finite. So therefore all this Chernoff business works, right? So it's not only different, it's almost diametrically opposite, right? Here sub-exponentials are heavy tails, in the statistics community sub-exponential distributions are like. So this is not something that this dichotomy has existed in a while. You just have to know which sub-exponential people are talking about depending on which. Okay. So we'll stop here and maybe meet back at 4, and I hope you'll excuse the 5 minutes less coffee break. Hi. Oh, I know of you. I never met you.
Yeah, I think you are interested in
More. Yeah.
He's at Stanford. Yeah, I think you did some total 18 years.
Yeah.
Yeah.
That's how I
That's where the sub-exponential thinking. And I learned from being the expert and all that. Then when I said sub-exponential, which is sorry. No, it can't be true. And I showed that book and then you opened up your thesis.
Okay.
This is.
Yeah, there is. This also goes back several decades. So this is.
I don't know who did it, but it's just confusing. It's an
old abuse.
Yeah, I think pre-internet era maybe they didn't intersect and all.
I'm guessing that probabilists versus statisticians, but I'm not sure.
But this all this terminologies are done by probabilists only, right? Not queuing folks or something.
Yeah, queuing folks who then work with heavy. So when you're working, so it turns out that most of the analysis with heavy workloads and queues that tends to be done for regular variation rather than numerical. So it's not as commonly used in the queuing literature. Queuing literature is regular variation concept, but in the context of when probabilists study random walks, exceedance properties, there they use.
Yeah, because this has nothing to do with queuing. You're just saying that the sum is like one. You can apply it to queuing.
So you kind of so for example, if you remember Ridley's recursion. So Ridley's recursion basically tells you that the workload can basically be thought of as basically a sum of IID random variables. So those random variables even in queuing, you can these kind of sums will come up organically, but they don't come up in exactly this form. You usually have some boundary, some positive part of the sum or something.
Yeah, but n things, whatever you did, right? F of that I'm used to derive a concentration number also.
Right.
Yeah, that like with that small O also. Yeah, assuming some sort of still in the older, the other.
Right.
Yeah, well, it's cool. Yeah, yeah, you want to move on for coffee? Yeah. Slides are not.
What to talk to?